Sum of forces. In the simplest sense, it's by the parallelogram rule of addition. If we have two forces, here we go. If we have two forces, and we want to find the sum of those two forces, we draw a line through the beginning and end of one force parallel to the second, draw a line through the beginning and end of the second force parallel to the first, and the resultant, the sum of those two forces, goes from the common origin to the opposite side. If you would rather think in terms of the triangle law of addition, we place the second force at the end of the first, and then the sum, the resultant, goes from the beginning of the first to the end of the second. If we end up with a right triangle, that is, if the two forces that we're trying to add together are perpendicular, we can use simple sines and cosines. Most often we end up using law of sines, law of cosines to find the relationship between the lengths of the sides and the angles of the resulting triangles, the resulting vectors. The next was dividing forces into components. When we're dividing a force into components, we need to know how many components and what directions those components are. So if this is the force that we want to divide into components, and we're told that the two directions that we're interested in are these two directions, these might be directions which we have access to and can exert a force. We want to pull the object in that direction, but we can't get there. There's something in the way that we can't get there, so we have to pull in these directions. These are directions we can get to. So what are the components? Well, it's the same thing. We draw lines through the beginning and the end of the vector parallel to the first direction. We draw lines through the beginning and end of the vector parallel to the second direction. And the sides of the resulting parallelogram are the components that we're looking for. And again, typically we end up using law of sines, law of cosines to find out what those components are. If we have rectangular components, for rectangular components, the two directions that we're working with are perpendicular to each other. So let's say that this is the force whose components we want. Now, just because we say rectangular doesn't mean that they have to be x and y. So I could say I want the rectangular components along and perpendicular to this direction. When we talk rectangular components, I only have to tell you one direction. The other one, by definition, is perpendicular to that. So the other direction, by definition, is perpendicular. But again, we draw lines through the beginning and end parallel to the first direction, through the beginning and end parallel to the second direction. And the sides of the resulting parallelogram are the components that we're looking for. Since we now have a right triangle, we can use simple trigonometry. Sine of the angle is opposite over the hypotenuse. Cosine of the angle is adjacent over hypotenuse. And we can find the sides that we're looking for. When we're adding forces, we could divide each of those forces into their rectangular components relative to a common coordinate system. I could find the components of the first force relative to horizontal and vertical. I could find the components of the second force relative to horizontal and vertical, and simply add those components together to get the resultant or the sum of both of those. And if we have more than two forces to add together, that's certainly the way that we're going to want to go. So the first part was finding sums and components, adding vectors, dividing vectors into components. The next thing that we looked at was calculating the tendency of a force to cause rotation, and that was given by moments. We're looking for the tendency of a force to cause rotation, so in 2 dimensions, if we have a force acting at some location, so here is a force acting at this location, and I want to know the tendency of that force to cause a rotation around this point, say point A. What I'm doing is I'm imagining that the paper is nailed down at that spot, and if the force is applied, how is it going to make that paper rotate? What is the tendency to cause rotation? And the moment of the force about point A has magnitude of the force, perpendicular distance between the line of action of the force and the point that I'm taking moments about. If I want the tendency of the force to cause a rotation around point B, I have to think in terms of the line of action of the force. We can slide the force along this line of action without changing its effect on the body. So the magnitude of the tendency to cause rotation around point B is going to be, again, force times perpendicular distance. So that's the perpendicular distance between point A and the line of action of F. Here is the perpendicular distance between point B and the line of action of the force F. Of course, one is going to make the body rotate in one direction, the other makes the body rotate in the other direction. If A is the fixed point and the force acts, it causes this object to rotate counterclockwise. Whereas if B was the point that is fixed and the force acts to push in that direction, it's going to cause this object to rotate clockwise. So if you calculate the moment in this simple fashion, moment equals force times perpendicular distance, you have to keep track of the direction of the rotation yourself. You have to look at it and say, what direction will it rotate about point A when that force is applied? What direction will it rotate about point B when that force is applied? If the perpendicular distance is not easy to find, then we can divide the force into components, and typically we use rectangular components for that, and we can calculate the moment of each of those two components separately and add those two together. We have to keep track of, do they both cause it to rotate in the same direction, or do they cause it to rotate in opposite directions? So that was Varignon's theorem. The moment of a force is equal to the moment of its components about the same point. Or another way of calculating it is with the cross product. When you use the cross product, it's always R cross F. It is never F cross R. The magnitudes of those two cross products will be the same, but the sign will be opposite. If one gives a positive value, the other is going to give a negative value. The directions of the cross product are going to be different, yes?
Is it assumed that clockwise is negative, counterclockwise is positive on the test? Or do we have to show that counterclockwise is positive, clockwise?
I guess I would rather have you tell me the strength and then clockwise or counterclockwise in 2 dimensions, and then neither one of us has to guess. When we use the cross product, as long as we use a right-handed coordinate system, so this is the x direction, the y direction, right-handed coordinate system says if I start with the fingers of my right hand in the x direction, curl them to the y, my thumb points in the direction of the z-axis. So in this case, the z-axis is going to have to come out of the board. And in 2 dimensions, when you perform this cross product, you're going to get a number k. In 2 dimensions, there will never be an I component, there will never be a j component. And a positive k then is going to be a counterclockwise rotation. Negative k would be a clockwise rotation. So using the cross product, it tells us the direction, and if you indicate it as plus 37k or negative 37k, there shouldn't be any confusion. That's a perfectly good way of representing it. But in 2 dimensions, I find, just tell me which direction it's going to rotate. And there's little or no confusion about that. When we get into 3 dimensions, the cross product is pretty much the only reasonable, simple way of calculating the moment. It's possible. I've seen people do it. You see professors do it all the time, but students typically have a little harder time until you get used to it. It's possible to divide the force into its x, y, and z components, calculate the rotation around x, y, and z axes for each of those separately. But what I find is most often, students especially, and sometimes even faculty, will lose a force. They'll take the moment of one component about one axis and forget that it also causes rotation about another axis. So it's easy to lose things. In 3 dimensions, I would strongly recommend the cross product as the best way to go. We had moment about a line. And to find the component of a vector in the direction of a line. So component of M in the direction E. So E is going to be a unit vector, a pure direction. We take the dot product of the vector M with the unit vector E, and that will give me the component of M. Actually, it's a rectangular component. It does not give me these non-rectangular components. It gives me the rectangular components of the vector. And when we say a moment has a magnitude and a direction, the direction is the axis about which that causes the rotation. So when we find the component of the moment vector in the direction of E, that is how strong is the rotation around that line E. So we had moment about a line. I guess the next thing was couples. A couple is a pair of forces, equal magnitude, opposite direction. So we have a vector F. We have another vector which is the negative of the first vector. When I ask what is the combined effect of these two forces on the body, the sum of forces horizontally is 0. They have no net tendency to push the body horizontally. Sum of forces vertically is 0. They have no net tendency to push the body vertically. And no matter what direction I choose, the net force in that direction is going to be 0. However, if these two forces do not act along the same line of action, they will have an effect to cause a rotation of the object So the effect